Now, to some extent, we've seen this before. Remember, in a question on differentiation, there was a table of values, f of x as a function of x. You basically made a curve fit using a polynomial, and once you had a curve fit, you could then differentiate that curve to get the first, second, and whatever derivative was asked to. This is something similar. So we'll have the polynomial fit, and we'll look at some other ones too. Okay, so exact fit is what we did when we talked about differentiation. Here we might be given some points, say 1, 2, 3, 4. So what we did was we assumed a polynomial which would ensure that that curve, that polynomial, will pass through these points. So these are given points, and then the black line is an exact fit because it passes through all the points. Okay, so this is usually happens when you have a few data points, but normally, so this is, let me just call that f of x and x. Normally what will happen is, if you do an experimental process and get data, you'll see that you'll get lots of points, something like this. Sometimes at the same point, you might get two data points, like this point up and down are at the same x coordinate. Now, in this case, what you would do is you try to find a best fit line, something like this. So it not really passes through all of them, but it sort of is the best line which can explain the data. So this is the inexact or approximate fit. You could also call that best fit. So this is a line which captures the trend, but it doesn't quite pass through all the points. So we'll talk about both these fits in this particular chapter. Okay, the last thing we would look at in this chapter is interpolation and extrapolation. Okay, so for example, if you knew what was the temperature at, let's say in this room at 10 o'clock, 11 o'clock, 12 o'clock, then you can predict from that data what would be the temperature at 10:30, 11:30. That would be an interpolation. However, if you're trying to predict what would happen at 1 o'clock when you had only data from 10 to 12, that would be an extrapolation. And so both those things are clearly important. So the best way to explain this is through a plot. So if you have, let's say, data 1, 2, 3, you did a best fit curve. With this curve, you can predict what happens at this point. That will be an interpolation. And then we don't have data here beyond these points. That would be an extrapolation. That also can be done quite easily once you have the equation of the line. Okay, let's get to some of the methods to obtain an exact fit. So the first one is something we've seen before. We can use a polynomial to fit the data. So exact nth order polynomial. Okay, so here's how we proceed. Given n plus 1 data points, so let's say x0, y0, x1, y1, so on till xn, yn. Note that those are n plus 1 points because we started with the index 0. So if you're given these points, then we can use an nth order polynomial to fit the data. So let's see how this is done. So here is an nth order polynomial. Say y is f of x equals a0 plus a1x plus a2x squared, so on till an xn. So there are n plus 1 unknowns. But we know that this curve, which we assumed, passes through those n plus 1 data points. So what we do is we sub in the value for each of those points. So substituting the data into the polynomial, we have yi equals a0 plus okay, we can do it this way. y0 equals a0 plus a1x0 plus a1x0 square plus so on an x0n. So that would be the first point. Then we have y1 equals a0 plus a1 x1 plus a2 x2 square plus so on an, sorry, my bad, this should be x1 x1n. So get the idea. You keep doing that till you reach yn equals a0 plus a1 xn plus a2 xn square plus so on an xn square. So how many equations do we have? Well, we have, this is the first equation. This is the second one. And you keep doing till you have the n plus 1th equation. So now what we can do here is we can collect all the terms which are known. So remember, x0, x1, x2 are numeric values. y0, y1 are numeric values. So you can put them in. And what will happen is these will be equations with unknowns a0, a1, a2, and so on. So what I'm going to do is I'm going to rewrite this equation as a matrix equation. We're just going to switch the order. So it's written as 1, x0, x0 square, x0 cube, so on, xn, sorry, x0n. Then we have 1, x1, x1 square, x1 cube, x1n. We just keep doing that till we reach 1 x n xn square xn cube xnn a0 a1 so on till an equals y0 y0 y1 so on till yn. Okay, note that this is a matrix here. This is a n plus 1 cross n plus 1 matrix. Everything in that matrix is known because x0 will be a numeric value, right? You know the data x0, you know the data x1, and so on. Everything here on the right side is also known. It's n by 1 vector. And these things here, the a's, are unknowns. Yeah, so if you want to think of this as, let's say, A, this matrix, we can call this small a equals B. Then we can solve for A using one of the methods discussed earlier. Okay, some of the methods are Gauss-Jordan elimination, Gauss-Seidel, and so on. Matrix inverse, and so on. Okay, so what we've been able to do effectively is obtain the unknowns a's, which means that we can now compute the polynomial y. And once we have the polynomial, we can then do interpolation, extrapolation. Okay, so let's see an example. Okay, so this will be like a review of what you've done in the past. Here is an example. Given the following data, x equals 0, 1, 2, y equals 2, 0, 4, and the rate polynomial fit y of x. Okay, so how we go about? Well, we see that there are 3 points, so we need n equals 2, a0 plus a1 x plus a2 x square. Substituting the values, so we have 2, 0, 4. So 2 is the first one when you put x equals 0. So a0 plus a1 0 plus a2 0 square. Then we have 0 on the left. That's when we put x equals 1. a0 plus a1 1 plus a2 1 square. Then lastly we have 4 equals a0 plus a1 2 plus A2 2 square. Just going to go ahead and make the substitutions and see what I get. A0 plus A1 plus A2. This will be A0 plus twice A1 plus 4 times A2. So 1, 2, 3. Okay, so from 1, okay, let's just do it the way we wrote it down. That might be easier. So we can write this as 2, 0, 4 equals A0, A1, A2. Okay, so now I need to find the first row here. So A0 is the only non-zero term. So we'll have 1, 0, 0. For the next one, we have 1, 1, 1. Next one, we have 1, 2, and 4. So we need to invert this matrix and solve for A's, right? So what I did that for you. A0 is 2, A1 equals minus 5, A2 equals 3, and so we have y equals 2 minus 5x plus 3x squared, and that's our final answer. Yeah. Yes, so there are three data points. Okay, and so we need a polynomial of order 2, right? Because a polynomial of order 2 has 3 unknowns. Wait, but that's good. You're asking questions. So if you have questions, please ask me. No, don't feel bad about asking questions. Yeah, this is very similar to what you did for one of your mock questions, the third one where you had this data set and you did this. So this is not new. This is well done. Now, the problem with this, not problem is, the only thing you need to do here is you need to invert that matrix. Okay, and think of what if you had like a 1,000 by 1,000 system. So I give you 1,000 data points. So then it will be cumbersome to do it. Of course, if there's 1,000 points, then you probably won't use a polynomial fit. There are better ways to do it. But if you did do it with polynomial fit, then it's a big, big matrix to invert. So that's where the next method comes. It's called Lagrange polynomial fit. But it is a smart way of writing the same equations, same order equation, but it's a smarter way. Let's look at the next one. It'll save you some, it will avoid doing this inverse. Okay, so let's look at the next method. It's called Lagrange, whatever you like to call it, interpolation. Okay. This method also uses nth order polynomial for n plus 1 data points, but uses a different approach, a different form for the polynomial. Okay, so the best way to illustrate this is probably to show you, well, some example with just 3 points. So here it is. Consider 3 points: x0, x1, x2. So instead of having n points like I had for the previous case, Let's look at 3 points. Let's say these map to y0, y1, y2. Okay, so clearly there are 3 points. That means we need second order polynomial, right? That's what we've seen in the past. So what we do is, the way this Lagrange method works is it assumes this polynomial, a0, x minus x1, x minus x2, plus a1, x minus x0, x minus x2, plus a2, x minus x0, x minus x1. So just look at that expression, see what's going on. So for the first one, you sort of ignore the x0 and do x minus x1, x minus x2. Okay, second one, you ignore x1 and use the other two. And then for third one, you ignore x2 and use that. Now, if you expand that out, if you expand this out, that's a second order polynomial. If you do the same thing over here, that's a second order polynomial. This is a second order polynomial. So we do have a second order polynomial, just that it is assumed in a very different format. Okay, so what is the advantage of writing the polynomial in such a complex way? It turns out that it makes your life easy when you want to find the coefficients. Okay, so this polynomial passes through this polynomial passes through x0, y0. So let's just compute. Let's just see the consequence of substituting x0, y0 in this equation. So we have y0 equals a0, x0 minus x1, x0 minus x2. And look at the second and third equation. When you put x equals x0, those two will just be 0, right? Because there's x minus x0 sitting in both of them. So be 0 plus 0. So here we have a0. It's nothing but y0, x0 minus x1, x0 minus x2. Okay, now we can do the same thing with other coefficients. A1 is going to be y1 divided by x1 minus x0, x1 minus x2. And a2 will be y2 divided by x2 minus x0, x2 minus x1. Okay, you see that you did not have to invert anything. It's just flows from the way the polynomial was assumed. So that's why this is probably a slightly simpler way of getting the coefficients. Okay, so our exercise goal now is to use this expression to compute the formula for the same problem and see if we get the same formula for the curve as we would for this one. Okay, let's redo the same problem using a Lagrange polynomial fit. So example. Given the following data points, x equals 0, 1, 2, and y equals 2, 0, 4, generate a fit using Lagrange interpolation. Okay, let's do it. So x minus 1, x minus 2, I took these two. Then we have a1, x minus, I take 0 and 2. So x minus 0, x minus 2, plus a2, x minus 0, x minus 1. Okay, so why don't you try computing a0, a1, a2 yourself? Let's see if you can do it. So sub in, substitute 0, 2. So I took 0 from here, 2 from there. So it will be x0, y0, 1, 0, x1, y1, and 2, 4, x2, y2, and solve for a0, a1, a2. Yeah, I'll try doing that yourself, and then I'll solve the problem after that. Let me know if you what do you get for a0, a1, and a2. Yeah, I got 202. Let's check what. Okay, we can quickly check that. It's not a very hard problem, right? So let's put y equals 0, a0, 0 minus 1, 0 minus 2. This gives a0 is 0. Wait, I did a mistake. My bad. X is so. This is 2, right? So this should be 0 minus 1, 0 minus 2, y is 2. So x, y is 2 here, x is 0. Is that right? No. One. Next we have x equals 1, y equals 0. So I put, clearly this first one will be 0. Let's look at the second one. So y is 0, x should be 1, 1 minus 0, 1 minus 2. Has to be 0, right? And then last one is x is 2, y is 4. So 4 here equals a2, 4 minus 0, 4 minus 1. Yes, you're right. My bad. 2 minus 0, 2 minus 1. You get 102. Okay, so that's not, we're not done yet. Let's see what the expression looks like. So A0 is 1, x minus 1, x minus 2. Next one is all 0. So it doesn't matter what's here in the brackets. A2 is 2, x minus 0, x minus 1. Let's try to simplify this. We have x squared minus 3x plus 2. This is all things 0 plus 2 times x squared minus 2x. So we can see that it's 3x squared minus 5x plus 2. Okay, so you should write it in this fashion. This is your answer. Okay, so we've got an expression for the curve, a polynomial of degree 2, but we also solved it using a polynomial fit. Let's check this answer against the one we got. So 3x squared minus 5x plus 2. Remember that. So 3x squared minus 5x plus 2. So the answer is the same. The difference being that just by assuming that formula, the way it is, Lagrange is written, you do not have to invert 2 by 2 or 3 by 3 matrix. So there's some advantage of using a Lagrange interpolation.